Today we're going to be starting chapter 3, and for our first part of chapter 3, we're going to be talking about the limit definition of the derivative and then learning some of our basic derivative rules. So before we can really talk about a derivative and what a derivative is, we have to kind of get there. We have to say, okay, how do we go from limits, why are limits important, to then getting into derivatives? So let's start by talking about slope. So if I have a nice linear equation, I ask you at any time to find the slope, like right here. What's the slope of this line at this point? Okay, well, you could do your rise over run. Okay, and you would get a slope of 2. You could pull it out of the equation. Slope is equal to 2. If I ask you to find the slope at any point along this line, it should always be 2, right? It's a constant slope. It's nice and easy to pull slope from a linear function. Okay, we've done slope before with linear functions. What if I asked you to find slope on this quadratic equation? Well, you'd be like, well, Mr. Arbone, quadratic equations don't have slope. It's not true. Okay, quadratic equations do have slope, but their slopes are different depending on where you are on the quadratic equation. And what does slope represent? Well, slope represents a rate of change. So depending on where I am on my quadratic equation, my rate of change might be a little bit different. Okay? So now that we've kind of established that quadratic equations do have slope, how do we go about finding one? Well, we can kind of combine the idea of finding a slope from a linear function with this idea of finding the slope at a specific point. Not just the slope everywhere on the function, but the slope at a specific point. So we call this line that I drew right here, this kind of slope at a specific point, our tangent line. And we call this rise over run, this slope over 2 points. We would call that a secant line. Now you're probably wondering, Mr. Arbone, why are we bringing trig into this? Well, hopefully you remember from geometry that a tangent line is just any line that's tangent to a curve. Okay, usually use them with circles. You have little tangent lines sticking on the edge of circles. Well, we can use them for any curve in calculus. A secant line is just another way of its average line. It's the rate of change over an interval, while a tangent line is my slope, my rate of change at a point. Well, I can find my secant line. Yes, I can pick any 2 points on a curve and I can find the change over that point. Well, what mathematicians, what those who were kind of discovering calculus saw was that, well, if I started to move my secant line points closer to the point where I want to find my tangent line, over time, the secant line that I found was closer and closer and closer. The slope of that secant line was closer to the slope of the tangent line. So as my secant line moved closer to my tangent line, their slopes became closer in value. And eventually, they became so close in value that we could essentially say they're the same thing. Now, what did we just learn about in calculus where we're moving closer and closer and closer to a value? Well, that was limits. So mathematicians discovered that as I move closer and closer and closer, secant line to tangent line, I could evaluate the slope of the tangent line. So they came up with an equation for this, and that is the limit as delta x approaches 0. And that delta x stands for the change in x. So as the change in x approaches 0, as in this little change in x right here of my secant line, as it gets smaller and smaller and smaller, as it gets so small that it's almost 0, so I'm evaluating it of f of x as x plus delta x minus f of x divided by delta x. Okay, so this is a really weird equation, but let's break it down. Okay, remember your delta x or your change in x or that slope. Slope is rise over run. Well, these f of x values, those are y values, which is our rise. And this delta x, this is our x value. Okay. Now, these specific y values, this is the y value at, tangent line. This is the y value for my secant line. So what's happening is I'm evaluating it as the change in x gets closer and closer to 0. So I'm shifting these two functions closer and closer together. So I'm getting my rise, my change in y, closer to my run. So I'm moving these two equations closer to each other until they're so close that they're essentially on top of each other. And that allows me to evaluate the slope at that point. Okay. Now, long-term, big kind of idea, you don't really need to know this equation. This is kind of our discovering derivatives, but we're not going to use it forever. We're really going to kind of learn it today and then not really worry about it. But we can still practice with it. So I want to find the slope of f of x equals x squared plus 3 at the points 0, 1 and -1, 2. So I would say the limit as delta x approaches 0 of 0 plus delta x squared plus 2 minus 0 squared plus 3. So what you might notice is that I took my x value here and I plugged it in for x in my function, f of x, and then delta x went in for delta x. So this first one is I'm plugging x plus delta x in. So I put 0 plus delta x because 0 is my x and delta x is here, plugged it in for x. My second equation, I'm just plugging in x for x. So that's where I get the 0 squared plus 3. So this is f of x. This is f of x plus delta x. And that is all over delta x. And now I can simplify a bit from here. So this becomes the limit as delta x approaches 0 of delta x squared plus 2 minus 3 all over delta x. Oh, I'm crazy. I don't know where I'm writing plus 2 here. This should still be plus 3. So then 3 and 3 are going to cancel out. So I get the limit as delta x approaches 0 of delta x squared over delta x, which becomes the limit as delta x approaches 0 of just delta x, because delta x squared and delta x, I can cancel out of delta x, which is just equal to 0, because I can finally plug in my 0. So my slope at the point 0, 1 is 0. Okay, which, if you know anything about your parabola, it's that nice swoopy parabola shape. And what should my slope be down here at 0, should be a slope of 0. So that lines up. Okay. I'll let you try the other one on your own, and then I'm going to post the work here in a sec.